Functions represent some of the most powerful aspects of the R language, and they really represent the transition of the user of R into the kind of programmer of R. And the basic idea is that you can type the command line and kind of explore some data and run some code, but eventually you'll probably get to the point where you need to do something a little bit more complex, a little bit more that can be expressed in a single line or maybe in two lines. And if you have to do this over and over again, then you're usually going to want to encode this kind of functionality in a function. I'm going to talk about functions in three parts here. First, I'll talk just about the basics of how to write functions and how they're written in R. Then I'm going to talk a little bit about lexical scoping and the scoping rules for the R language. And then last, I'm going to end with a little example. So functions in R are created using the function directive, and functions are stored as R objects just like anything else. So you might have a vector of integers, a list of different things, a data frame, and then you have a function. So in particular, our functions are R objects that are of the class function. Okay, so the basic construction here is you assign to some object. Here I call it f. The function directive, which will take some arguments, and then inside the curly braces there is R code, which does something that the function does. So one nice thing about R is that functions are considered what are called first-class objects. So you can treat a function just like you can treat pretty much any other R object. So importantly, this means that you can pass functions as arguments to other functions. This is actually a very useful feature in statistics. And also functions can be nested, so you can define a function inside of another function. And we'll see what the implications of this are when we talk about lexical scoping. So the return value of a function is simply the very last R expression in the function body to be evaluated. So there's no special expression for returning something from a function, although there is a function called return, which we'll talk about in a second. So functions have what are called named arguments, and the named arguments can potentially have default values. So a lot of these features are useful for when you're designing functions that may be used by other people. And for example, you may have a function that has a lot of different arguments, so you can tweak a lot of different things, but most of the time you don't have to change all those different arguments. You may only care about one or two. So it's useful for some of the arguments to have default values. So first of all, there's the formal arguments, which are the arguments that are included in the function definition. So if you go back to the previous slide, the formal arguments are the ones that are included inside this function definition here. The formals function actually takes a function as an input and returns a list of all the formal arguments of a function. So not every function call in R makes use of all the formal arguments. So for example, if a function has 10 different arguments, you may not have to specify a value for all 10 of those arguments. So function arguments can be missing, or they may have default values that are used when they're not specified by the user. So our function arguments can be matched positionally or by name. So when this is key when you're writing a function, and also when you're calling it. So, for example, take a look at the function SD, which calculates the standard deviation of a set of numbers. So SD takes as input x, which is the name of the argument, which is going to be a vector of data. And there's a second argument called na.rm, and this controls whether the missing values in the data should be removed or not. And the default value is for na.rm to be equal to false. So by default, if you have missing data in the set of numbers for which you want to calculate the standard deviation, the missing values will not be included. So here I'm simulating some data. And I'm just simulating 100 normal random variables, and there's no missing data here. So if I just calculate SD on the vector, it'll give me an estimate of the standard deviation. If I say x equals my data, that's the same thing. So here I've named the argument, but I haven't. Otherwise the data are the same, so it'll calculate the standard deviation. In the first example, I didn't name the argument, so it defaulted to passing my data to be the first argument of the function. So in the next example here, I'm going to name both arguments. I'm going to say x equals my data and na.rm equals false. That calculates the same thing as before. Now when I name the arguments, I don't have to put them in any special order. So for example, I could reverse the order of the arguments here, say na.rm equals false first, and then say x equals my data second, and that'll produce exactly the same results because I've named the arguments. Now what happens if I name one argument and don't name the other? Well, what happens is that the named argument is set, and you can think of it as being removed from the argument list. And then any other things that are passed will be matched to the function arguments in the order in which they come. So, for example, SD, after we remove the n8.rm argument, only has one more argument left, and so my data will be assigned to that argument. So all of these expressions return the same exact value. So although it's generally all these expressions are equivalent, I don't recommend all of them equally. So, for example, I don't necessarily recommend reversing the order of the arguments just because you can, even though if you name them, it's appropriate. So, just because that can lead to some confusion. So positional matching and matching by name can be mixed, and this is quite useful often for functions that have very long argument lists. And so, for example, the LM function here, which fits linear models to data, has this argument list here. So the first is the formula, the second is the data, and then the subset, the weights, etc. And you can see that the first 5 arguments here don't have any default values. So the user has to specify them. But then the method, the model, the X argument, those all have default values. So if you don't specify them, they will use those values by default. And so the following 2 function calls are equivalent. I could have specified the data first, and then the formula, and then the model, and then the subset argument. Or I could specify the formula first, the data second, the subset, and then say model is equal to false. Now the reason why the first one is okay is because I match the data argument by name. You can imagine that that's kind of taken out of the argument list now. Then y tilde x isn't specified by name, so it's given to the first argument that hasn't already been matched, and in which case that's the formula. Model equal to false, so that's been matched by name, so I can kind of get rid of that from the argument list. And then 1 through 100 has to be assigned to the argument that has not yet already been matched. So in this case, formula was already matched, data was matched, and so the next one is subset. So 1 to 100 gets assigned to the subset argument. So this is a somewhat confusing way to call LM, and I don't recommend that you do it this way, but I wrote it this way just to demonstrate how positional matching and matching by name can work together. A common usage for LM, though, is the second version here, which say LM y tilde x. So there's a formula there, and then the next one is my data, which is the data set that you're going to grab the data from, the subset argument, and then so the first 3 arguments, are commonly specified every time you call LM. But then the rest you may or may not specify, and so if you just want to specify one of the following arguments, it's easier just to call it out by name. So most of the time, the named arguments are useful on the command line when you have a long argument list and you want to use the defaults for everything except for one of the arguments, which may be in the middle or near the end of the list. And you can't usually you can't remember exactly which argument it is, whether it's the 4th or the 6th or the 10th argument on the argument list. And so you just call it by name, and that way you don't have to remember the order of the arguments on the argument list. Another example where this comes in handy is for plotting, because many of the plot functions have very long argument lists, all of which have default values, and you may only want to tweak one specific argument, and so it's useful not to have to remember what the order of that argument is on the argument list. So function arguments can also be partially matched, which is mostly useful primarily for interactive work, not so much for programming. But when you call a function, if the argument has a very long name, you can match it partially. So you can type part of that argument name, and as long as there's a unique match there, then our system will match the argument and assign the value to the correct one. So the order of the operations that R uses is, first it'll check for an exact match. So if you name an argument, it'll check to see if there's an argument that exactly matches that name. If there's no exact match, it'll look for a partial match, and then if that doesn't work, it'll look for a positional match. So here's a function with 4 arguments, A, B, C, and D. So A has no default value. B, C, and D all have default values. And so when you define a function, you to both specify the names of the arguments and whether or not any of the arguments have default values. So null is a common common value to assign to an argument, which can mean a variety of things, but it usually means that there's nothing there. So one of the key features of the R language is what's called lazy evaluation. So lazy evaluation is a common model in a variety of programming languages. And the way that it works is that all the arguments to a function are only evaluated as they're needed. And so, for example, if you take a look at this function over here, you can see it takes two arguments, a and b. But the body of the argument only does one thing. It takes a and it squares it and then returns it. Now recall that in a function, the return value is whatever the last expression is that's evaluated. So there's only one expression in this function, so that's the last expression. And so it's the return value. So if I say f of 2, what happens? Well, in R, what happens is you get 4 because 2 squared is 4. Now you might be wondering, well, what happens to b? When I call f, I never specify what the value of b is, and furthermore, b doesn't have a default value, and so what happens? Well, what happens is nothing happens, because the function f doesn't actually use b, and so the argument is never evaluated, and so because it's never evaluated, there's really no error, there's nothing that's going wrong here. Now you might say that, of course, well, the function f is kind of poorly defined, so why would you give an argument where that's never actually evaluated, and that's a reasonable objection. But in this case, the function will operate correctly because because the value of 2 is positionally matched to the argument a, which is then squared. Here's another example of a function that's only slightly more complicated than the previous one. So this is another function that takes arguments a and b, but now what the function does is it prints out a and it prints out b. And so when I call f of 45, look what happens. I get an error that says in print b, argument b is missing. So here, what happened is that it printed out 45 because 45 was matched to the argument a. And so there was no error up until the first line of the function. There was no error occurring. But then when it got to the second line, it had to evaluate the argument b. And because b had no value assigned to it and no default value, then an error had to occur. So here, but you notice that the error only occurs after the 45 was printed out, and so the lazy evaluation implies that because the argument is only evaluated when it's needed, everything else that comes before it, if that's valid, then it will execute until it hits the part which causes an error. So there's a special argument in R functions, which is the ... argument, and it's used to indicate a variable number of arguments that can sometimes be passed on to other functions. So the 3 dots are often used when extending another function, and you don't want to copy the entire argument list of the original function. So for example, you might want to extend the plot function, and just to have a little bit of a tweak or to change some of the defaults, for example. And so for example, you might create a function that's called myPlot, and the myPlot will replicate some of the arguments of the original plot function, like x and y, but it's going to change the default type argument so that instead of creating circles for points, you want it to create lines. So you say type equal to L. But of course, the default plot function has many other arguments, and you want to leave them all to be the same. And so what you can do is you can pass ... and then that can be used to kind of absorb all of the other arguments in the plot function. And then what happens is I'll take the ... and then pass it down to the original plot function. And so all those original arguments can be preserved, and I don't have to retype or reconstruct all of those arguments in my extended function. There's another use of the ... argument, and it's for what are called generic functions, so that extra arguments can be passed in methods. So we'll talk a lot about more of this later when we talk about object-oriented programming. But the basic idea is that in R there can be special functions called generic functions which don't do anything, but what they do is they dispatch methods for different types of data. And so the ... is used very heavily in this type of setup. So lastly, the ... argument is necessary when the number of arguments that are passed to a function cannot be known in advance. So one good example of this usage is in the paste function. So the paste function, what it does is it concatenates a set of strings together to create one string or a vector of strings, and it can take a variable number of arguments. So there's no way for the function to know in advance how many arguments it's going to have to paste together, and so the first argument for paste is actually ... and therefore you can take a number of different R objects that are character vectors and then paste them together using a separator and which the case the default is the space. So there are other arguments to paste, which are sep and collapse, but they come after the ... argument. Another function that has as the first argument is cat, and what cat does, similar to paste, it pastes together a number of strings, but then it prints out the concatenated string either to a file or to the console. And so you can see there are many other arguments to cat, but the first argument is going to be the set of R objects that are going to be concatenated. So one catch with the ... argument is that any arguments that appear after the 3 dots on the argument list must be named explicitly, and furthermore cannot be partially matched. So you can't use positional matching or partial matching for arguments that come after the 3 dots. And this kind of makes sense because otherwise there's no way for R to know whether you're passing something to the ... or whether you're passing something to a different argument. So if I say in this first example here, if I try to paste together A and B, so A and B are going into the ... argument, and then I say sep equals colon, which means that I want to paste them together by separating them into with a colon. However, if I try to do partial matching with sep, what happens is that the partial matching gets ignored, and so when I say paste A, B, and then SE equal to colon, well, the SE is in another circumstance might be partially matched, but in the paste function it can't use partial matching, so it just ignores that and just assumes that colon is just another string to be pasted together, and so then you get the string AB colon. So just be careful when you're using functions that have ... as an argument, that any arguments that appear after the 3 dots have to be named explicitly and in full.